Okay, thank you very much, and thank you for having me and for the introduction. Right. So the title of my talk is.
You don't need to wear a mask when you're speaking.
Oh, is that the okay. All right. So in Michigan we wear masks when I was speaking, so it's a bit. Okay, this is much easier. Thanks for pointing. Okay, great. So the title of my talk is, as Sam said, Motivating Action and Coherent Homology of Hilbert modular varieties. And I think that probably this is the most difficult part of my talk, is just getting through the title. And after that, things are much easier. So let me just give you an idea of what this general line of work is about. So the starting point is the observation that some automorphic forms contribute to various cohomology theories, can contribute to multiple, I guess I should say can contribute, not all of them do, but they can contribute to multiple cohomological degrees, multiple times. And there is sort of a series of work, so all involving actually Venkatesh and some with collaborators. So there's also my advisor, Kartik Prasanna, Michael Harris, Alesius, and then well, there are more other works that are more recent, and they very vaguely say that there is some deep arithmetic reason that explains this phenomenon for x. So this is just sort of the setup. You're trying arithmetically to explain this these multiple contributions from the perspective of the Langlands program. So on the sideboard over there, I wrote out the Langlands program just very intuitively, that one side you have automorphic forms, on the other side you have Galois representations, and very vaguely you're trying to say that you have these multiple contributions to cohomology on this side, and you're looking for something on the other side that could explain it. Okay, and so my work is in the case of studying a similar phenomenon in the case of Hilbert modular forms. So this is the automorphic forms in question are Hilbert modular. So this is just a bird's eye view of what's happening. But the first sort of easiest example to see this phenomenon is just for modular forms. So the first part of my talk will just be on modular forms of weight 1. Okay. So let's say we have a modular form. Let me start with a modular form. So this is a holomorphic modular form. Let's say for now it has weight k bigger or equal than 1. So the first thing I want to do is just remind you how to interpret such a modular form algebraically. So it has an algebraic interpretation as a section of a line bundle. And then just over the complex numbers, the way this looks is you have H mod gamma, where gamma is some congruent subgroup. And your modular form is not quite invariant under the group gamma, so it doesn't define just a function on here, but rather it defines a section of a certain line bundle. So you can give yourself a copy of C and then quotient by gamma. And the way you want to act on a pair Z comma tau is on the first variable, of course, you act, so if gamma is A, B, C, D. So this is just supposed to encode the equation that modular forms satisfy. So on the first variable, you want to act with AZ plus B over CZ plus D. And then the second variable, you just encode CZ plus D to the K. And then a modular form would just define a section of this. So I don't know if that's a good color. Okay, so of course I can send Z to the pair Z comma F of Z. This action will encode the the equation that modular forms of weight K satisfy. Okay, and so this is some interpretation. It's not quite algebraic yet, but if we want to make it algebraic or even rational, let me just say that you can upgrade this to working rationally. And so you'll have some X, which is a curve over Q. This is going to be the modular curve. And then above it is a certain line bundle, or you can think about it as a sheaf, and I'm going to write omega to the power K. So it's really the kth power of omega, which is the Hodge bundle. So anyway, the point is that this has some algebraic definition, and what you get out of this is that the upshot of all of this is that F really defines a section of this line bundle. And all right, so if I assume that the Fourier coefficients of my modular form are all rational, then it really defines a section over Q. If the Fourier coefficients are in some extension, then I should tensor with that extension here. But for simplicity, let me assume for the sake of the talk that the Fourier coefficients are just rational. So let's assume that all the APFs, so the Fourier coefficients are rational. So I'm taking some normalized eigenform, like normalized cusp form, and then I'm assuming that the Fourier coefficients are rational just for simplicity. Okay. So that's one, and then here it's omega to the power K. I guess if I'm working with okay, it's omega to the power K, and then perhaps eventually I'll set K equals 1. Okay. So here are some facts that deal with the higher coherent cohomology classes. So I sort of said that you'll see some multiple contributions to multiple cohomological degrees. So let me just tell you what happens in this simple case. So I can write a very explicit class here. So I'm going to take a complex conjugate of the variable. I'm putting a minus in front of it to go back to the upper half plane. And then I'll multiply this by y to the k. And I'll look at dz wedge dz bar over y squared. And one can check that this actually defines a Dolbeault class. So I gave you this picture over here, and the point is that if you compute how gamma acts on that particular thing, you can compute sort of with what weight it acts. And once you do this, you'll realize that I'll call it omega f infinity, because somehow I'm doing something at infinity. And this will land sort of, it will be a 0-1 class with coefficients in the line bundle with weight 2 minus k. Okay. But of course, I can interpret this using the Dolbeault theorem in terms of maybe the analytic, in terms of the analytic cohomology. And then I can use Gaga to finally go to H1 XC omega 2 minus k. So in the end, what I get is a class in the sheaf cohomology of this line bundle weight 2 minus k. And then the point is that the Hecke action will act on this higher cohomology class with the same eigenvalues as it did on the original class. So one way we can say this is that omega f infinity belongs to H1XC omega 2 minus k, and I'll put a little subscript f. And what this will mean is this is just going to be all the classes, let's say eta H1XC omega 2 minus k, such that if I act with TP on eta, I get AP times eta, where AP are the Fourier coefficients of f. And so it acts, the Hecke correspondences acts with the same eigenvalues of this class. Okay, and then the final thing I want to say just as a closing is that these are all the contributions to coherent cohomology. These are all contributions of this Hecke eigensystem. So I'll just write of F to coherent cohomology of these automorphic vector bundles. Okay. All right, so this is how the classes work. And so you can see that there's no coincidence. So in other words, so this section belongs to omega k, and then this other class belongs to omega 2 minus k. And so somehow the degeneracy will happen exactly when k is equal to 1, right? Because then these two line bundles are actually the same line bundle. Okay, now I wanted to say how these forms fit in the Langlands program. I'll try to explain to you how go from there, what to do from there. Okay, so in terms of the Langlands program, if I take F to be a modular form of weight k bigger or equal to 1, then associated to it are Galois representations. So they should be representations of the absolute Galois group. I'll take GL to QL bar. So L here is going to be some prime, not dividing the level. But you get such Galois representations. So this was, I guess, done by Eichler and Shimura when k is equal to 2. Then by Deligne when k is bigger or equal than 2. And then when k is equal to 1, the story is a little bit more complicated. And this was a paper by Deligne and Sir. And so the point is that, and let me just, so let me talk specifically about about k is equal to 1. So the point is that, so if I take F to be a modular form now, and its weight is k is equal to 1, then it actually does not contribute to singular cohomology. Okay? Or to the cohomology of any local system. So it only really makes these contributions to coherent cohomology that I talked about. And because of that, this Galois representation, rho f, so it will actually be an Artin representation. So it will go L over Q, and I can take it to GL to C, and it's an odd Artin representation. But here, the point is that it's constructed somehow using so it's constructed a little bit differently because it does not contribute to singular cohomology. And on the other hand, when you look at, as I explained, if you look at coherent cohomology, it actually contributes twice to the cohomology of the same line to H star X omega F, right? Or maybe for now over the complex numbers, but let's just write it like that. So it makes two contributions over here. And here I'm just going to say, I mean, I already sort of wrote it down, but let me just say that it factors through a finite quotient. So a finite extension L over Q, finite Galois extension like this, right? And so the goal is sort of to draw a relationship between these two things. So goal is sort of to understand how these things are related. The fact that the Galois representation is degenerate in some sense, because it factors through a finite quotient, and the form makes multiple contributions to the cohomology of the same line bundle. Okay, so let's just see how this works. So let me now continue from there and suppose that k is equal to 1, because that's the case where where this degeneracy happens. So one question you could ask is this class omega f infinity in H1 XQ? So is the class itself rational? And okay, of course, I wouldn't have set things up this way if the answer was yes. So the answer is no, the class is actually not rational, but actually it's easy to see what multiple of this class is rational. So however, if you divide it by the Peterson product of f of itself, if I divide it by the Peterson product, I will get a rational cohomology. So you can see this using Serre duality. Okay, so this is true. And now the key point here is that this Peterson product can be expressed in something in terms of L. So let me write that Stark's conjecture sort of allows you to express the Peterson product in terms of a log of a unit. So for the Artin representation, okay, and here we don't quite take the representation of f itself, but what we take is the adjoint representation. So the adjoint representation of rho f, it says something like this, or you can use Stark's conjecture to deduce this, that the Peterson product of f of itself is some constant times the log of the unit. And this constant is sort of innocuous. It will be, for example, rational if the Fourier coefficients are rational. So by the way, if I'm assuming still that the Fourier coefficients are rational, then sort of Stark's conjecture is known in that case by the work of Stark himself. So I can ignore the assumption of Stark's conjecture here. Okay, so we get that the Peterson product is actually related to some log of a unit. And then so I should tell you what this U is. So let me call it actually UF. Okay, so UF is in some group UF. Okay, I know that's not very helpful yet. Okay, and so this UF is actually so this is a Stark unit group. And I can tell you how it's defined. So UF is just going to be, you can define it as follows. You can look at sort of Galois invariant homomorphisms from the adjoint representation to the unit group. And I'm going to tensor everything with Q for now to simplify things. So it turns out you can compute that it's one-dimensional, and then you can pick, let's say, a generator there, and then you'll get such a statement. Okay. All right, so let me just show you an example of what this might actually look like in a simple setup. So here's an example. You could consider this imaginary quadratic extension of Q, which you adjoin square root of -23, and you can consider its Hilbert class field. And it turns out that it's a degree-free extension of that in the Galois S3. Okay. So I could describe it a little bit more explicitly, so let me do that. So there is a subfield here, which I'm going to call K, and K is going to be Q adjoint alpha, where alpha is a root of polynomial x cubed minus x squared. Okay. And then L is just the Galois closure of K. So that's how so that's how you can think about L. Okay, so I've given you a Galois group Galois of L over Q, which is S3, and the point is that there's just one, irreducible two-dimensional representation of S3. So you can take that representation, right? So you can take rho to be S3 to actually Q, this to be the unique irreducible two-dimensional representation. It turns out that it's an odd Artin representation if you think about it that way. Okay, so then And there will exist a modular form. One could write it down explicitly, but from general theory, one knows that there exists a modular form, f of weight 1, such that its Galois representation is actually this row, that representation here. Right, so in terms of the Langlands program, I guess I defined for you something here, and I'm saying it's coming from some weight 1 form. And then I want to tell you specifically what this unit group is, just so, because it looks kind of mysterious, and I want to make sure that you're not too scared by it. So this unit group will just be UK1. So these will be just the norm one units of the number field K. The number field K actually has signature, where's K? Here. It has signature 1, 1, and this will be a rank 1 group. And you look at the norm 1 units there. And actually it's alpha here, the alpha that is the root of that polynomial is a generator. Okay. And finally, this assertion about the Petersonian product is that the Petersonian product of f of itself is 3 times this log of the unit. Well, the unit, as I said, is alpha. So you take that root, and you can look at its value, this log, and it turns out to be related to the Petersonian product like this. Okay, so that's an example of how this proposition works out. Okay, and so the point is that this somehow provides the connection between the two sides, between the two contributions there and this sort of motivic side of the Langlands program. So let me clean this up into one statement. Okay. Trying to deliver these forms for the first time. Let's hope that this is working. Okay. Let me go over here. Maybe do this about modular forms of weight 1. So this. Okay. So this leads to a proposition or maybe a corollary of this. So you can state it neatly like this, that there is a graded action of the exterior algebra on this rank 1 unit group. I'm saying something quite fancy. This is nothing else as a copy of Q, because this is a rank 1, this is a one-dimensional vector spaces. So in degree 0, you just get this, and then in degree 1, you get the dual of that unit group. So I'll say something about the duality in a second. So there's a graded action on this, on the rational contributions to cohomology of F. Okay, so such that a dual unit actually UFV and UFV acts by. So it should go from, right, it's a graded action according to this grading. So it should go from H0 XQ F to H1 XQ omega F. Right? And so it's going to send my form F, which was here, to the form omega F infinity divided by the log of the unit. And somehow there's some duality here to be fixed. So this is the dual unit, and somehow this is some, so let me just say that there is like this, and this is dual technically to UF. And there's some way to fix this where UF here corresponds to this UFV here. Okay, so here's maybe a good time to mention something about the fact that this is the dual unit group. So in this context, the point is that if you act with a unit and you want to divide by the log of the unit, somehow if you rescale this unit, it will actually just rescale here in the denominator, which is not good because the action would not be linear. So in this very simple setup, the duality accounts for the fact that you're dividing by this number. And then, so when you rescale the dual unit, it will sort of rescale the unit by 1 over that number. And because it's in the denominator, it works out to be linear. So it's nice to see it very explicitly here, but it also fits sort of very well with these this general framework where it's usually this dual motivic cohomology group that acts, and sort of this is, according to this general framework, the right thing sort of to act. Okay, so let me just remark at the end here is that what we got is that F itself generates all the contributions to cohomology, H star, XQ, omega F. So all these rational contributions are generated by F over the exterior algebra. Okay, so in other words, the goal that we set out to achieve over there is sort of achieved. So we explain the contributions to cohomology using something on the Galois side, the Galois representation and the unit group associated with that. Okay, and so, okay, so if there are any questions, please let me know. But okay, so
how do you prove this proposition?
Sorry?
What does this do to?
Oh, well, I checked this, but I'm not sure how. How much this is quite simple. So
I mean, it's an observation. I'm just curious if there's a history.
Yeah. So the point is that this is sort of a rephrasing of this proposition that just sort of relates the Petersen product to a constant times the logarithm of the unit. And I think in the original work of Stark, there was an observation like this already for some special case. And then this is just a matter of sort of relating the Petersen product to the adjoint L value, and then saying that Stark's conjecture says that it should be the log of the unit. So it's sort of based off of Stark's conjecture is a simple observation, and I think it was like in some special case already observed by Stark in that series of papers. So. And then like this statement is really just like a restatement of the simple fact to match up with the general framework to see it sort of neatly like that. Any other questions?
Can I ask a question?
Yeah.
So this add zero, so that's reducible.
Right. So I'm sorry, I went over this a little bit fast. So add itself would be the action by conjugation on the 4-dimensional space, and there you can look at the subspace of trace zero matrices. Okay, so it's a 3-dimensional subspace, and that's irreducible. So when I write add zero, I mean the trace zero 2x2 matrices and an action of conjugation on that, and that's irreducible. Yeah. Any other questions? Okay, so let me say what this is sort of motivated by the conjecture of Harrison Venkatesh, which is just doing something similar modulo p to the n. So so this one says something similar, so that there is a graded action of this exterior algebra like this. So, so I'll just say that I want to work sort of integrally. So before I tensored with Q, and for this purpose, I shouldn't have tensored with Q when I defined the unit group, wherever I did that. So here I just tensored it with Q for simplicity, but I shouldn't have done that. And here I should also take integral sort of cohomology. So I should take an integral model for the modular curve and so on. But I hope that's okay. So there's a graded action such that, and so they specify that modulo p to the n, sort of these dual units, so U of v acts by certain derived Hecke operators. So they construct operators on this special fiber, and they conjecture that those come from this dual unit group, and they give some numerical evidence for this. So this proposition is like the Archimedean version of what's happening there, modulo p to the n. Okay. All right, great. So my main goal is to talk about Hilbert modular forms. So I think now is a good time to switch to Hilbert modular forms. Okay, so the point now is to run the same sort of story, but for Hilbert modular forms instead of modular forms. So this will be sort of part 2 of the talk. So part 2, Hilbert modular. All right, so maybe I kind of wanted to say how they fit in the Langlands program, but it sort of got crowded over there. So let me just do that here. So Langlands. So we have the automorphic forms here, and here we have the Galois representations. So, so let's take F over Q to be, for simplicity, I'll take it to be real quadratic. I could take it to be any real extension of, totally real extension of Q, but we take it to be real quadratic just for simplicity of notation. And so, so F will be a Hilbert modular form for this real quadratic extension. And it has now two weights. Weight K1, K2. So both of these integers K are bigger or equal to 2. And I think so I should assume that they're congruent to each other in mod 2. Write that down. So sorry, both of these are bigger or equal than 1. Okay. So what do the Galois representations look like here? So the Galois representations, I'll write again rho F. They're Galois representations of now F bar over F. So the absolute Galois group of F instead, and I'll still take them to be into Q, Q to QR bar. And this degenerate case that I'm interested in is when both of the weights are 1. Or at least that's the most degenerate case. And I can say something at the end about the intermediate cases, but let's see what happens so what happens when K1, okay, so let me take F of weight instead of K1, K2, I'll take K1 equals K2 is equal to 1. And once again, this will not contribute to singular cohomology, just to coherent cohomology. And on the other side of the Langlands program, you'll get this representation, which is a representation of some finite extension L over F. And you can, so it's an odd Artin representation like this, GL2C. And so this one on this side, sort of there, we had two contributions to coherent cohomology. And so contributes twice to coherent cohomology. And this one contributes 4 times. And 4 here is 2 to the degree of the extension. So if you wanted to know, for a general extension, it would contribute 2 to the degree of the extension times. To coherent cohomology. So, sorry, let's move this up for a second so we can write more comfortably. I wanted to just say, so F itself is a section of, again, the Hodge bundle. And this I can take over Q. And then for H1, there are going to be 2 forms, omega F1 and omega F2, which contribute to H1, X over the complex number omega. And there'll be the 4th contribution, which is sort of F12, X2. Okay, so these are the 4 contributions. And if you remember, I described for you quite explicitly what for a weight 1 modular form, what the contributions to higher coherent cohomology are. So let me just show you that the whole point is that a Hilbert modular form, you have 2 variables. So I make complex conjugate at the first variable or the second variable or at both. And that's what those contributions are. So here specifically omega F1, for example, is going to be F where I complex conjugated the first variable, but I left the second variable alone. And then I'm going to take some decoration similar to before for things to work out. Y1 squared. So that's what the omega F1 looks like. And omega f2 is similar, but I do that at the other variable instead. And omega f1, I do it at both variables, and I get an H2 class. Okay, so these are the 4 contributions to cohomology. Okay, I made sort of a mess out of this. But okay, so the goal is the same, which is to try to use the unit, so sort of use something about this Galois representation to explain these contributions to cohomology sort of rationally. Okay, so let me take a second here to describe this goal. So the goal is sort of to explain contributions, sort of rational contributions. So contributions of F to H star X Q omega. So I'm just writing Q to specify using sort of the Galois representation factors for a finite extension L over F to C, where now L over F is finite. Any questions about just the goal here? Water. All right. So let me try to do this. So what we need is the analog of this unit group that we had before. So let me state a proposition that sort of computes the rank of this unit group or describes it in some way. So now the Stark unit group, so I can define it in the same way. So UF is going to be just the homomorphisms from the Galois group of L invariant under the Galois group of L over Q. And here I'm going to take the trace zero adjoint representation and to UL. So the Stark unit group, it actually has rank 2. So in general, this 2 is actually equal to F over Q. So in general, it will have the rank equal to the degree. Okay, and sort of there is an isomorphism, which is in some sense natural, but I don't really want to say exactly what that means, but I want to say that there's an isomorphism between this dual group, tensor C, with some two one-dimensional subspaces. So there's sort of, if you tensor with C, you get 2 natural lines where this dimension of over C of U F on V is equal to 1. Okay, so it has rank 2, and it has sort of, once you tensor with C, it has distinguished line, 2 distinguished lines like that. Okay, so the point is that we'll again define an action, which then we're going to sort of say how it should interact with rationality. So define an action of this. So let's say both of these, so j equals 1 and 2, but by, okay, so I'm gonna, so if I want to go from H0, x omega f to H1, xc omega f, I'm gonna send f to this omega fj. Okay. So that means I complex conjugate at the variable corresponding to that decomposition. So this is conjugate at zj. Class was defined, if you remember up here. Okay, and so the point is that these classes are not going to be rational. And so which classes are rational? So this will be this conjecture that I stated. So the conjecture is that via the isomorphism, via taking the rational units and then looking at them embedded into this tensor C, And then looking at this isomorphism plus the other guy. Okay, so via this guy, it's this rational subspace of the dual units that acts rationally. So this guy acts rationally. So in other words, if you want to know which H1 classes will be rational, you're going to take like a dual unit here and trace it through this isomorphism and see what linear combination of that class you get, and that will be a rational cohomology class. So, so when I say rationally, I mean on sort of rational cohomology, right? So, this guy. So let me show you what this might look like in practice, although the statement becomes a little bit more complicated. Okay, so let me just say, so in particular, let's say this allows me to identify conjecturally, so can identify classes in H1, which should be rational. So I'll give you an example of this class. So there'll be some 4 units, U22, U21 and U22 in the unit group. And the kind of class that will be rational, I'll call it eta 1, is going to look like this. So I'm going to take log of this unit. I'm just trying to really give you an idea of what this will look like, but I know that I'm not saying exactly what these things are, but 2 divided by, and then here there will sort of be a determinant coming from all the logs of the units. So we log U11, log U22, minus log U12, log U21. So this is the kind of classes that will be rational, and then there'll be another class eta 2, which is defined similarly, which is rational. Okay, all right, so this is a rather complicated rationality statement, and at this point I wanted to make a remark that, so originally I had sort of a different rationality statement. Let me just mention this now. So in case we're looking at the current version of the paper, this is sort of an updated version that is going to be out very soon. So remark. Okay, so one is that the previous version of the paper, which is now like, I'm about to like post the newest version, but so there was a different rationality statement which implied this statement that there's some lambda j, which I will see, such that these multiples of omega fj are actually rational. So it was a much simpler statement. There was no like linear combination. It was just sort of that you divide by some log of the unit and you get a rational number. And so this statement seemed suspicious to some people. So for example, Gyugen was one person that pointed out that maybe this is not the kind of thing that one would expect, that a certain multiple like that is rational. And other people were also worried about this, like Akshay, for example. So what turned out is that you have to be careful when you trace through this isomorphism. And originally when I wrote it down, I sort of incorrectly assumed or like computed that the matrix of this isomorphism will somehow be diagonal and that there'll actually be 2 units. But so this is in this proposition. These are really like 2 sort of dual units, and you have to be careful. So there's no 2 units, there's sort of 2 dual units, and there's actually like 4 actual units, and you have to take all of them into account. So so I just want to sort of remark on this that, right, so this version no longer implies, okay, so So this version of the conjecture is, doesn't imply this. Just some people. Second thing I wanted to say is just what the use of studying such a thing is, or what my motivation for studying this was. So I really had in mind when I started on this project. So I had in mind maybe some potential applications to special values of L functions, or specifically I was thinking about p-adic L functions. And what happens is that sometimes you need integral representations that rely on these kind of cohomology classes omega f1 and omega f2. Not sure why I wrote them that. Okay, so these omega f1s and omega f2s, like over here, they come up in some integral representations, and they define sort of periods. So you want to know what multiples of them are rational, and this comes up. So you have this higher cohomology class, and you want to know what multiples are rational. So for example, this is employed in recent work of Leffler, Piloni, Skinner, and Zerbis. This kind of higher coherent cohomology argument, higher Hidefire argument. And so, you land with the question of understanding, which of these omega f1s, omega f2s are rational, and it turns out, now it turns out that maybe no multiple of them is rational, but you have some specific combination. So I wanted to leave this out there. I wanted to also say that I also have a sort of mod p to the n version for Hilbert modular varieties. So that's more similar to the conjecture of Harrison Venkatesh, but there it's very difficult to get evidence for the mod p to the n thing, because the evidence in that work relies on some very explicit computations, which don't seem to be available in the Hilbert case. Okay, and the last thing I wanted to say in terms of remarks is that this sort of begs the question, can you do similar things for other Shimura varieties? And it seems that there is some work also of Gyujin, who has been working on the Siegel case, and I've been also thinking on some things about some things related to that. So it seems that there's a lot of hope for maybe seeing what the generalizations of this conjecture to other Shimura varieties should be. Okay, how am I doing on time? Let's see. Okay, around 10 minutes. Is that right? Perfect. Okay, so any questions at this point?
What is n here? Qn, any n?
Right, so you can, n is just any integer, yeah. Okay, right. So one other remark I should say is that it would also be nice to have maybe like a p-adic version of this. So there's a mod p to the n version, but it's not easy to patch it together to some p-adic thing. So that's another thing that is sort of missing maybe from the story. Okay, so I think at this point I wanted to talk about the evidence for this conjecture in the last 10 minutes. So we have this conjecture that says that this unit group, once you trace through the isomorphism, that's what's going to act rationally, and you can make specific predictions on what cohomology classes will be rational. Okay, so so let me just to fix idea. So what are we getting? So actually, sorry, I wanted to say, first of all, this is going to be part 3, which is going to be on the evidence for this conjecture. And so let me just summarize what we're exactly trying to get evidence for. So the thing is that, so we define some cohomology classes. And I'm calling them, so over there I wrote eta 1. So let me write eta 1 and eta 2 to be these classes. And for now, we just know that they live in H1C. And I have this eta 1, 2, which lives in H2 C omega. So this eta 1, 2 lives over there. And so the question, right, that we're trying to amass evidence for is, are these classes in rational Q? So are they actually rational? So this seems quite difficult to answer in general, but let me first state what I can prove in this direction. So the first, I'll state this is the theorem. So first of all, I can prove that this class eta 1, 2 is an H2 x cubed. So I'm going to assume Stark's conjecture when necessary. So again, if the Hilbert modular form has rational Fourier coefficients, for example, then we don't have to assume it because it's known, but otherwise we're assuming. So first of all, this H2 class is rational. So if you're thinking about the unit group action, this means that sort of the highest degree of this exterior algebra acts rationally. And the other thing that I can prove is that if I look at this eta 1 and eta 2, these are a priori classes in XC, and this gives some basis. Okay. So what I can prove is that the determinant of this basis so we don't know that the actual elements are rational, but if you look at their determinant and compare it to a rational determinant, they'll be the same.
And in H1.
H1.
Thanks. Yeah, in H1. Okay, so that's as far as I could get with this. And so the remaining question is still about these H1 classes. So the remaining question is eta 1 and eta 2 in H1 x cubed. So these ones still need to be settled. And so here is an idea. So the idea is to look at an embedded modular curve. Okay, so you could consider some YQ embedded in XQ. Where this is a modular curve. So you can consider an embedded modular curve. Let's call this embedding iota. And then you can look at, sorry, just a bit easier. So you can look at the restriction of these cohomology classes. So you can look at the restriction of eta j, and this will land in H1 YC. And then you pull back the line bundle as well. So you'll land over here, and you can ask whether the restriction is rational, right? So then you ask, so the question is this restriction actually in H1 Y cubed? And so this is not so bad to test because this line bundle actually pulls back to the canonical bundle, and it makes sense to integrate this class. I mean, that space is one-dimensional. So I should say that the whole trouble with this business is that this H1 space is two-dimensional. And when you do this restriction, it's one-dimensional, but there's a downside to this whole process. So let me first say what the downside of doing this is, and then what the upside is. So let's say the drawback of this approach is that this restriction of eta j is 0 unless, or it's expected to be 0 at least, f is a base change of some weight 1 modular form. So that's the drawback, that by restricting to embedded modular curve, you can only detect rationality for things that actually came sort of from that modular curve, in some sense. But nonetheless, so suppose we are in this setup. So suppose f is the base change of f0. Okay. Then let me first just state what the conjecture looks like, because I can state it a little bit more explicitly. So suppose this is the base change. So then conjecture is the following, or is equivalent. So one has to do a little bit of work, but you can show that it's equivalent to this simple rationality statement that if I take the sum of the two classes divided by the log of the unit associated to f0, then that will be rational. And also if you take the difference between the two cohomology classes divided by the log of the, so now it's a slightly different unit, and I'm going to write omega f0f. So it's a twisted unit. Okay, so if I take the sum of the two classes and the difference of the two classes, then that scaled by a log of a unit is actually rational. So this is the conjecture that these are rational. Okay, and further, I could check that this is equivalent to just the single rationality statement that the integral of the restriction of one of them, let's say eta 1, is depend over q cross. So there's some constant in q cross, or okay, let's just do q cross, maybe q bar cross just to be safe. So so the restriction of just one of them should be so here I went to write omega f1 should be log of this uf0. Okay, so somehow when you have two classes here, but there's some extra automorphism in this case, which allows you to reduce it to a single rationality statement like this. Okay, and I'm probably out of time. Let's see. Okay, 2 minutes, perfect. So just continuing from here. So what I did is I managed to sort of develop some explicit formula for this integral. Okay, so the formula, so I developed and implemented an algorithm. To compute this integral of this restriction of omega f sigma 1 and over yc. And then this gives some evidence for the conjecture, in the base change case, evidence in some cases. So for example, I could compute these integrals using some formulas, and then I would check whether there is a rational number such that they're equal to the log of the unit, and I could get up to 15 or 20 digits of accuracy that it's like 1/3 times the unit or 5 times the unit. So it's quite convincing given the sizes of these things. Okay, thank you very much for listening.
Are there any questions for Alex?
How are these units?
These two units, what are they exactly? Right, thanks. So the two units is that the first one, UF0, is just this unit, well, UF0. So you just take HOM from at 0 row to the unit group. The second one, the thing is that the representation you have to take, so UF0F will be in so it will be in the HOM space where you take this and you twist it by the quadratic character associated to the extension. And you look at that going to the units. And so, so the omega f over q is the quadratic character associated to f over q. So it's that's what it is. It's a little bit odd, but that's what comes out of the machinery.
So to follow up on this, then how do you see this generalizing to a general, take a general totally real extension and talk about modular forms there?
Yeah, so it doesn't, right, so you don't get such a simple statement. So
presumably some matrix of logs of units.
yeah, you'll, even in the base change case, you will still get one like a matrix. I mean, so general F over Q, let's say in the base change case, certainly what will be true is that, so this is F still a base change of some F0. So one thing that, for example, I can prove is that the sum of the all omega Fj divided by the log of the first unit will be rational. Okay, so the sum ends up being rational. But then the other rationality statements are a little bit more complicated, and they really depend on basically if the extension is Galois, you can sort of look at the action.
Are you assuming it's rational in the state? Sorry, that it's Galois in the statement?
Yeah. So in the first statement, I'm not assuming that it's Galois. So the sum will always be rational, but I'm saying that the general statement will be slightly so the other statements, the other, D-1 rational classes, they will still be like slightly more complicated and involve some logs of units. What I was trying to say is that you can sort of look at the action of the, if it was Galois, let's say. So in a case where it's Galois, you look at the action of sort of GQ, right? You look at the action on like the on the Galois group, and you have to look at sort of that representation. So the permutation, so what will happen is you actually get just the like permutation representation of the group acting on itself, and in the real quadratic case, that one factors is like the identity, like into two characters, the identity and the omega F over Q. And over here, it will always have the subspace where the sum of the coordinates is fixed when you act with the Galois group on itself. And then, but then the complement of that might be more complicated in general. So it sort of all depends on what Galois extension you have or what the Galois group of the closure is or something.
Does it have something to do with just the finite dimensional representations of the Galois group of F over Q?
Yeah. So, so with a specific, with like the permutation representation of that Galois group. So for example, if that Galois group is abelian or something, then you get like a simple statement, but in general, you get more complicated statements, even in the base change case.
So just the Galois group acting on itself.
That's right, yeah. So, right, yeah. So you sort of, you act with the Galois group on itself, and like the sum of the of all the so you pick like names for all your things for your elements of the Galois group. The sum of those is always invariant under the Galois action, so that's fine. But then you have some other, the representation will decompose in some way, and that will lead you to understanding of all the rational cohomology classes. But it's just a little bit more complicated.
Yeah, maybe you could just say a few more words about your algorithm.
The algorithm? Yeah, absolutely. So the algorithm, so what this looks like is you want to take the integral of this kind of form that I wrote down. So Z1, Z2, Y1, DZ1, which so you've embedded to a diagonal modular curve. So it's actually Z and Z. So you really you're looking at this. And this is an integral over, H mod gamma. And so, and this is so it's some non-holomorphic object. And so there's a theorem by Paul Nelson. So,
Sorry, that's me. Yeah.
I'm so sorry. Yeah, we never met. I'm sorry. So
I wasn't asking the question for that reason. I didn't know this.
Oh, I see. This one, you're not just messing.
That would have been smart.
So you have okay, perfect. So you have this theorem that if you knew the Fourier expansions of some even analytic function, then you have a nice formula for that. And so I use that formula in, well, for, I write down the Q expansion of this. And so one thing that goes into it is figuring out the Q expansions at all the other cusps of this thing. And that's another thing that I had to figure out. But yeah, okay, nice to meet you then.
I'll then go to bio dinner tonight.
Don't worry, I did the same thing with Shahidi in the talk.
Oh, okay.
Are there any other questions? Anything from Zoom, perhaps?
So if there are no more questions, let's thank Alex one more time.